for helping us out. As you saw in the agenda I had shared, and as Jim's got here, Jim's leading our high aluminum percentage aluminum gallium nitride project. And as we had briefed as we kicked off this overall meeting, really looking forward to both Jim and Changfei briefing everybody on what went into securing the award, what year one has looked like, again, just to give everybody a sense of what a awarded project looks like, at least through year one. And Jim, with that, I'll turn it over to you.
Okay, thanks, Mark. Thanks a lot. So I've been having Teams problems. So if you suddenly can't hear me, just let me know. I think you will, but I'll be able to hear you. You might not be able to hear me, and I have a backup computer ready just in case. So anyway, Mark, thanks a lot for inviting me to talk about this. It's definitely been an interesting year and an interesting project. So we have been working on a project called Advancing DoD High Power Systems, Transition of High Aluminum Percentage Alcan from Lab to Fab. And so this is the outline of what we got. So first I'm going to talk about I'm going to kind of bring you to where we are now and then go back from there. So I'll give an overview, an introduction, the team, and what we got done in year one. And then I'll make comments on what we did in terms of forming the team and writing a proposal, and then a few comments on project execution. And if you do win, which for the good or the bad, if you win, this is kind of what you can expect from at least our experience. So first, to give a background of our project. So our project is motivated by the electrification of everything. So if you look, here's the demand of power over the last, 25 years till now. You can see power demand was increasing this is electricity demand quite a bit, but the forecast is it's really starting to take off. And that's because of the electrification of everything. So if you look at cars are becoming electrified. So EV and hybrids we're now moving cars around because engines and transmissions are being replaced by in fuel tanks by batteries and a bunch of switches. And then people are putting data centers next to nuclear power plants because they need so much power. And of course, this isn't just true in the commercial area, but also in the defense. So ships has electronics everywhere. And in fact, there's a transition of electric drive, so analogous to EVs and integrated power systems. And then if you look at in aircraft, drones and aircraft have got electronics all over their flying computers with a ton of sensors. All of this takes electrical energy. And so within that context, power conversion, so the management and conversion of this energy is becoming more and more important. In particular, power switches are becoming really important. So let's just say, how does the power get to a data center? If you start from a grid, which is actually something like high voltage line, say 13 kV, that goes through a transformer and then goes down to 208 AC. And then there's a UPS system and an AC to DC converter to get it to 400 volts, and a DC to DC converter to 48, and then to 12 volts, and then to 1 volt. And in each of these, this is like the cumulative power loss. So first you have a total 3% loss, and 5%, 8%, 17%, and then 30%. So if you think about 30% of the power of all data centers are being consumed simply in the power electronics. So that's 6 times the amount of electrical power consumed by New York City in 2025. So there's really a need to make this more efficient, and that takes power electronics and particularly power switches. So if you opened up one of these power converters, and this is actually a smaller power converter, but you can see here's these power switches, and these are just high voltage devices that turn on and off and are efficient and can sustain high voltage, and then you put these in package. But typically the performance of these switches will limit the switching speed, the frequency of these, which then this is actually the inductor, which then affects the inductor, affects the entire size of the converter and size and efficiency of the converter. So power switches themselves, the technology for power switches is becoming really important. And then just to reflect again, this is not true in commercial systems, but this is certainly true in the military. So, and I saw this This is from WIPTA, a guy from AFRL gave a talk about this. So in a fifth generation fighter, there's 419 power converters and 46 motor drives. If you can make a technology to make every single one of these more efficient and smaller, it impacts the whole system. So power switches are critical, and they determine the converter efficiency size and also the heat sinking and therefore weight that's required. And so that's the context for our project. So our project is working on ALGAN, which is an ultra wide bandgap power switch technology. So I'm sure most people know that gallium nitride and silicon carbide have emerged in the last, say, 10 years and are really now having a big impact on systems. And this was a nice cover from IEEE, one of the IEEE journals, superpower devices. So you have the blue guy is GaN and the green guy is silicon carbide. And these have pretty quickly emerged and are being inserted into many systems like electric vehicles and a traction inverter and laptop chargers, and most people have probably used one of these, knowing it or not, in the last week or something like that. And these, GaN and silicon carbide, have a maximum electric field of 300 megavolts per centimeter, and there's huge investment in this area, both within the U.S. and also outside of the U.S. And so we can, as a country or as a company, we could choose to try to make better GaN and silicon carbide devices or cheaper GaN and silicon carbide devices. But this is taking another look. This is going to ultra wide bandgap devices. And I couldn't resist but to use AI to develop a cartoon of an ALGAN, the purple ALGAN man. And the point here is that the technological change is that you increase the aluminum fraction. So instead of a GaN channel, you have a high aluminum fraction channel, and this gives you a maximum critical field of 10 megavolts per centimeter. So the size of the device actually goes as 1 over the field squared. So if you have like more than a 3 times improvement in the critical field, you can increase the size of the device. So here you show, I have a cartoon of about a 10 times reduction in the size. And then you, roughly proportionately, as you decrease the size, you decrease the capacitance, and this allows you to make, in the end, smaller, more efficient power converters. And then in particular, ALGAN has a specific advantages because of the physics of transport through the channel at high temperatures. So ALGAN is also very good at high performance, small devices at high temperature. Now, luckily, the government was, I think, wise enough the U.S. government to start investing in this. I mean, the U.S. government really pioneered GaN and silicon carbide, 20 to 30 years ago, and they have been funding ALGAN, in particular ONR and Army Research Office have been funding ALGAN research, but this is in a lab today, and so this project is transitioning that from lab to fab. And so we formed what I think is a really good team to do this. It includes work in materials and device fabrication. So on the material side, we have the University of South Carolina and Asif Khan, and I'll say a little bit more about each of these groups later, but University of South Carolina, we have a startup, Ephemeron Labs, which is doing some interesting metrology work, Army Research Lab, and the Navy Research Lab, which is doing stuff on the material side. And device fabrication, South Carolina is also making devices, and MIT is making devices, and UConn is doing thermal simulations. And in general, this is all, say, in South Carolina, MIT, in the labs there. And in general, it's in small wafer sizes and relatively crude process technology. And so then we're transferring this to fab. So we're going from a 2-inch wafer to an 8-inch wafer, and that's important from an economics point of view because you get more die per processed wafer. But most of all, if you look around the world, most of the power factories are also often at 8-inch. And so this allows you to be compatible with effectively the manufacturing infrastructure. And then we're also transferring the materials. The epitaxy is really important to IQE, who is I think maybe the largest producer, independent epi producer in the world. And then in terms of device fabrication, we're transferring it to prototyping fabs at Lockheed Martin, which is a fab in Billerica. and then a Lincoln Lab, which is an 8-inch prototyping fab in Lexington. And also this coming year, as I'll describe, we're going to transfer to a commercial fab. And then we have a consulting company, Soundside Partners, who has a lot of experience in many different topics, who's helping us to coordinate this and tie it all together. But and ADI has a role of coordinating this and then getting involved in a lot of this work. But I think importantly, and to some of Mark's points, and I'll talk about in a second as well, we're also working to insert this into systems. So Lockheed Martin, I believe, is the largest defense contractor, and they're working to understand at a very early stage how this can help their systems. And then the ADI, how ADI is working, how can we develop the smart switch products, which will then allow the system insertion. And so ultimately, the goal is to make a 10 times better Algan switch, 10 times better than GaN today in a commercial fab, and then make it available for systems. And then here's kind of quickly marching through what we got done in this first year. So South Carolina had the epitaxy. So the epitaxy was originally grown on aluminum nitride on small wafers, and it's this area here, and it is on 2-inch wafers, and then IQE transitioned to this 8-inch Algan wafers and improve the crystallinity by about 3 or 4 times, and has line of sight to, we think, getting as good as being done at South Carolina today. And so this is the first, definitely in the program wants to see what exactly is being transferred. So this is, I think, the first transition of an 8-inch Algan epitaxy, world's first 8-inch Algan epitaxy, or for that matter, any ultra-wideband gap epitaxy. And then in terms of the materials also, we had a lot of development to improve the technology. So the technology was at a good level, but we have to keep improving it over time. So South Carolina reduced the contact resistance by about 4 times, from about 1 ohm millimeter to 4 ohm millimeters to 1 ohm millimeter. And then MIT made devices with really good specs, and I'll show that in a later slide of how they compare. And then I think importantly also on the epi from this 8-inch wafer, so we broke it up into pieces, and then MIT made devices with contact resistance of 4 ohm millimeter on that 8-inch epi. So this is as good as the starting point on 2 inches. So we made some good progress on the material side, and then we make some good progress on the device side. So in this case, we transitioned using the knowledge at MIT to Lincoln Labs 8-inch fab in Lexington. And we got through the process, and we made what we think is the first 8-inch Algan wafer that is ever made. So, or in fact, any ultra wideband gap FET on an 8-inch wafer, and this is just the completed device, and we're characterizing those devices now. And then we also transitioned this to Lockheed Martin. They have it's somewhere between, they can handle a variety of wafer sizes between 2-inch and 6-inch, but we transitioned the process there, and we're now ready to develop, their role is to develop the high temperature devices, and they transferred the process and measured devices up to high temperature, and really are prepared to optimize the devices for high temperature next year. And then this shows the benchmarking. So this is a plot of the switch size on the vertical axis. So 1 to 10, this is 10,000 times bigger of a switch, and this is a 10,000 times smaller as a function of the breakdown voltage. So you can see as you go up in breakdown voltage, the switch size gets larger and larger. And so you want to be down here. So you can see, and then here's the purple is what devices we made this year in this program. And then the blue is commercial GaN devices, and this is a zoom in. So we made devices which are about 2 times as small, so half the size for a given resistance as GaN devices. And then we have, the plan is by the end of the program to make something that's 10 times smaller. So a significant advancement over the state of the art today. And then this is just also what the other groups are working on. Ephemeron developed some dislocation imaging to allow us to be prepared for the commercialization and manufacturability and reliability studies. UConn did some really good thermal modeling, because as you shrink these things smaller and smaller, you really have to understand temperature limits. ADI, we did some cost modeling and some TCAD. Army Research Lab did the regrown contacts, which are important for the manufacturability or make a device design that could be manufactured. And then the Naval Research Lab is working on some diamond passivations, again, because handling the heat is really important. So in summary, we make GaN FETs that are 2 times better than commercial GaN today, though admittedly not qualified or anything like that, but just the raw R on area is 2 times better, and we see a scaling path to 10 times better. And we think the project's on track. So ultimately, the ambition is to make FETs which are significantly better than any power FETs today and made in a commercial fab, and the project's on track. And then here's where we're going in year 2. First, we're going to keep with the lab to fab. So we're going from Lincoln Lab, and then we're going to put this in an 8-inch commercial fab. And Lincoln Lab had not the unenviable position of struggling and dealing with a lot of the fundamental basic problems which goes from going from a small wafer to a big wafer really fast. And then we're going to use all that learning to then insert the technology into a commercial fab in the second year. And then we're going to continue on the development. So South Carolina and MIT are going to work on epi optimization and fields management to get us from a 2 times better device and hopefully, say a 4 times better device by next year. And then we're going to use all of the great equipment at MIT.Nano at 8 inches to start doing that work on 8 inches. So then it's directly relevant to the work that's going on in a commercial fab. And then Lockheed Martin is going to develop a high temperature version of the process. And then finally, we really are emphasizing and trying to, as fast as we can, insert this into real systems. So we're going to work with Lockheed to be making simulation models so that and then predicting the impact on systems and directly talking to the people who are developing these new systems. And some of the targeted areas are compact radar, where the power handling is really important, wireless charging, which requires a device with very high switching frequency and high voltage and power at the same time, and land-based small radar, and then in ADI looking into, can we actually be contributing to this problem with all the data center power? So we really do hope that we can be making a big impact on systems and really starting that transition soon. So that was sort of a quick summary of what we did for this year. And then here is the rest of the comments. So here's now kind of transitioning comments and forming a team and writing on the proposal. So I don't think I need to go over this. Mark went over it. So, but the problem is really we have all this great research and we got to get over the valley of death to try to transition it. And so this is the call for proposal, the topic that came out, and it was a lateral 3 nitride power switches, and it had all these success criteria, A, B, D, C, D, E, F, G, H, but it boiled down to, we want to make better lateral GaN FET than it has ever made before. We want to make it work at a high temperature, and we need to have a clear transition technology, and it has to be differentiated. In other words, when it transitions, it has to be helping the system in a significant way. And so we had submitted, ADI had submitted a topic which was similar to this in the goal, but different technologically. So we knew we were interested in the goal. So we decided to go ahead and work to try to get involved in this one. And then we had this brainstorming meeting January 5th, if I remember. And then by September, we had gotten the award was official, and it was about a month of writing. So the timeline wasn't that much different. And I think the in-person meeting, from my perspective, was super important because there was a very organic, how we got the team together was a very organic process. It wasn't planned or anything. It just kind of came together literally at that meeting. And then I think putting together a strong team, maybe obviously is really important, but we tried to have a different variety of organizations. So definitely having the transition partners, say Lockheed and ADI, that I think is really important. We had core, like literally world experts in the technology. So Asif Khan was the first person ever to publish a GaN HEMT in like 1993. And within a few years, I don't know many how, but certainly by 2000, he was already working on AlGaN. So definitely getting him involved was very useful. I mean, that was great. And Tomas Palacios is a very well-known researcher and has been doing great work in GaN at MIT for a long time. And then we had a number of these other groups are doing a great job supporting it. IQE, of course, is critical to this. You need Ephemeron to do this defect imaging, which in the long run is important. And then we have groups from the research labs and University of Connecticut and Soundside. So we had a pretty broad, we kind of have some of the core group and then, but also a broad group. And then in the proposal, you never know why you were chosen and why somebody wasn't chosen. Like, you don't really have any idea. But we did try to specifically target all of the success criteria. So you can see this is the first paragraph of the proposal, and we say we've targeted this success, A, B, C, F, C, E. So we tried to do every single thing that we can name. And then this also reflects that were named in the proposal. Then this also reflects what Mark said. I think what they want to hear, and I think you want to try to give them what they want to hear, but they really want to have a real transition project. Their antenna is up for something where you're going to do research and do great research. It may be great research, but that's not what they want to hear. They want to know how they're going to get into a system. And I've heard it should be called a lab to fab or to program of record, right? They don't want to say that just to get it to fab. They want to know exactly what system. You have a ship is going to be made in 2030, and you're going to insert it there. So maybe that's too optimistic, but that is what they want to hear. And then maybe, let's see, I have one more thing.
Hey, James, do you mind if I just make a quick comment there? And if those last two slides, I think, are really important, especially with what you just said. We keep calling this a team that's formed, which is very much what is being created. But when you look at, if you go up one more slide, if you look at what you've shown here and the individuals that are participating, it's more than just a team. This is a net new domestic value chain that is delivering this technology to the DoD for transition. So you have the folks that are helping support from, design, development, test, characterization, subject matter expertise, but also the supply chain partners there that are helping to do the fabrication and the actual production of it. Now, it's not at the scale, right, of what you might look at for commercial or full integration into a mission, but the value of what the Department of Defense is getting here is more than just the technology on its own or more than just a test, right? It's all of these partnerships together that are creating this domestic value chain. And if you guys remember back to the whole spirit of CHIPS, and whether it's reassuring or reestablishing the national capability to produce critical semiconductor microelectronics technologies here in the US, like this little snapshot here, I think, is just really important to highlight.
Okay, thanks, Ben. And then I guess the other comments on program execution, I think in the very beginning, we had an in-person kickoff meeting, and that was really helpful because from then on, who's doing what. And that was super important. We started this contract negotiation immediately. Like, that was a big hurdle. I think we had an organized high-level plan, but certainly didn't. And then we understand the details, but we didn't try to organize the details. We have weekly meetings, one with an all team and one just with the people doing the fab. And then the monthly meetings with the government are the main, from our point of view. There's a lot of written stuff that was sort of in theory you're supposed to do, but the critical things are, it's a monthly meeting with government, which is a lot of work. we put together more than 50 slides. It's an hour to hour and a half, and we split it up among team members. I talked to the CTE, the CETA lead a lot, and really he's been literally steering a lot of this. So definitely paying attention to this over time because they get a lot of input themselves. And I think NEMC has been great, and Mark and Emily, I've leaned on them a lot and asked a zillion questions, and they also get a lot of input and have to include it. And then I think then the last thing, I guess my advice is you want to apply for something that's really valuable to your organization, that you believe in and your team believes in. And I think that's because it is, from my experience anyway, it sucks a whole lot of your time. So if you don't really believe in it and your team doesn't really believe in it and your organization doesn't value it, it really is going to be a struggle. So you want to make sure that you really want to be putting a lot of your time into it. And I always liked this quote from Eleanor Roosevelt. And then at the same time, though, you have to be flexible because, you're taking the government money and they may be guiding you in something that's not perfect for what you want. It's got to be pretty close, but you got to give them what you want, or I think there's going to be difficulty. So anyway, that's all my perspective.
Great. Thanks, Jim.